Today's lesson, section 4.6, fundamental theorem of algebra. This is really a carryover from the last section, except what we will see is that our solutions that we find may be imaginary or complex in nature, and these problems may be a little bit more difficult to work through, but it's the same idea. So what I'd like everybody to do is consider, how do we solve this question? How do we find the zeros? Well, we got a problem. First of all, we can't factor that, so we have to rely on the rational root theorem. Let's go ahead and go to that. So it looks like P is 8. Let's write its factors. Q, the good news is Q is 1, which makes this a lot easier to do because its only factor is itself. So let's make a list of all of the rational numbers that are possible solutions to this problem. So we got 1 and -1, 2 and -2, etc. Those are all of our ratios that work. So that list is important to note. The solution is going to be contained somewhere within there. All right, next thing. Watch out for this problem. Notice there's no x to the 4th power term. When we do synthetic division, we're going to need a 0 to fill in for that coefficient. So we actually have 1 and then a 0. That's the 0x to the 4th. 1 for the x cubed, -2 for the x squared, a -12 for the x, and a -8 for the constant. Okay, there's our list. We don't know what number is going to work yet, but let's see if we can figure it out. We know there's going to be a 1 there. We know that's got to be 8 there to give us a remainder of 0. Who has an idea? What number might work? Let's try -1 if we heard that or not. That works. Let's remember the original degree is 5. So we need to write this as a depressed polynomial as 1x to the 4th minus 1x to the 3rd plus 2x squared minus 4x minus 8 equals 0. So now at least we know this. We know at this point -1 is an answer. Okay. Let's go back to this problem. Can we solve it? I don't think so. There's too many terms to use grouping. We need to go back to synthetic division. Let's drop down these coefficients. And try again. So if you cannot factor, you need to use synthetic division again and again and again until you get to something that you can solve or factor. So now we look at this and think, all right, what might work now? So I want everybody to think about that for a moment. Okay, sorry for the interruption. How about we try a 2? I'm thinking that might work. And it does. So now we know that 2 is a solution. Let's see if we can find the others. So the previous polynomial was x to the 4th. This needs to drop down to x to the 3rd plus x squared plus 4x plus 4 equals 0. Okay, now that once again, that's 4 terms. If you cannot factor, you're going to need to use synthetic division again. But this might be able to be grouped and factored. Let's try it. Let's take out an x squared. Okay, let's take out a 4 as the greatest common factor. Okay, this one will work. You see we have an x plus 1 as a common factor. And then x squared plus 4 remaining. We can solve that. Let's go ahead and do so. Let's take our first factor, set it equal to 0. That'll be -1. Okay, there's another answer. Now hold on a second. Let's go up to the list. Didn't we already use that? We did. So what that means is that's a double 0. We will list that in just a moment. The other factor is this. So if you move that 4 to the other side, you get a -4, and we need a square root. So do you remember what that looks like? First of all, it is plus and minus, which means it's 2 solutions. Square root of 4 is 2, but there's a negative under the radical, so that's an I. I think it's time we list all of these answers. Okay, let's go back up to the top. Remember we had a -1 and it appeared twice. So -1 is a double 0. And we're not going to worry about graphing these, but it's good to indicate that. We had 2, and then we had these imaginary numbers 2i and -2i. Now that would be 5 total solutions, including that double 0. If we go back to the original problem, point this out to you. See, the degree is 5. That means there's 5 total solutions. In this case, 3 of them are real numbers and 2 of them are imaginary, but there's 5 total solutions. Okay, let's try one more example. Once again, can't factor it. Let's use the rational root theorem. P is 12. Let's write the factors of 12. Good news, look at this. Leading coefficient is Q, and that is a 1. That will require a little bit less work. Let's get our list, which is going to be easy to do here, of possible rational numbers. Oops, that's a 2. That are solutions. Now remember, one of these will be a solution, maybe more, but there's no guarantee. And we see, let's identify this right now. Look at this, everybody. The degree is 3. Maybe 3 numbers from that list will be solutions. Maybe 2, maybe only 1. Something from there will be a solution. Let's drop down our coefficients. Are we missing any terms? No, we're not. 1, 7, 16, and 12. Okay, I want everybody to start thinking about what number might work in this situation. Mistake there, to give us a remainder of 0. So let's give everybody a chance to think about that and find something that might work. Okay, how about -3? Let's see what happens if we use that. It works. Don't know if that's the number you came up with, but -3 is a solution. Let's remember that. Let's rewrite this as a depressed polynomial. Our original power was 3, so this will drop down to 1x squared plus 4x plus 4 equals 0. Good news, that is a quadratic, so it can be solved in some way. Could it be factored? I think so. If not, you could use a quadratic formula. That would be fine. Need two numbers to multiply to give me 4, add up to give me 4. How about 2 and 2? Are you noticing something? That's a double zero. It occurs twice. Let's write our solutions. I see them right here. -3 and -2 twice. -2 is a double. That counts for two solutions. And I believe it was -3, wasn't it? Yes. Now that means there are actually three solutions, even though there's only two numbers. And when you go back up to the list, they're actually both in there. And that is your lesson.